She got her bachelor's at Oregon State and stayed there for 4 years working for PISCO and working on some projects in the Rocky Intertidal in New Zealand before she decided to go to graduate school. And so that's where I met Melissa. We were part of probably the best cohort of graduate students to go through the EED program in Santa Cruz. And so we started together, and we actually, I think, defended within weeks of each other. I think I brought food to her committee defense on the day I publicly defended. So it'll be great to actually hear what she's up to now. So after she got her PhD, she went to Stanford and worked at the Center of Ocean Solutions, where she got involved more in policy and kind of working on the bridge between ecology and getting ecological principles involved in management decisions. And now she's at USGS with a Mendenhall Fellowship, and she's going to be talking about her work there today on how the removal of the dam and sediment potentially coming downstream has influenced the nearshore.
Thank you, Gita, and thanks for having me. This will be fun. So just to acknowledge the other folks that I'm working with on this project from the USGS, the Lower Elwha Column Tribe, and Washington Sea Grant. So we know that disturbances can change the physical characteristics of landscapes, and quite fundamentally in some systems. So for terrestrial systems, we can think about things like wildfires or landslides. And on the aquatic side, we can think about disturbances caused by floods, waves from large storm events, as well as sediment dispersal and deposition. And these changes to the physical characteristics can cascade down into the whole ecosystem. So, for instance, we know that disturbances can influence the species diversity that we expect in a system. So frequent, large disturbance events tend to result in low diversity in the system. And similarly, infrequent, small disturbance events also low diversity in the system. And somewhere in between, we find this happy medium of disturbance and species diversity. And species diversity translates into things that are important for management and thinking about resilience of the system. And so we know that systems that are more species diverse tend to be more resilient to additional stressors and disturbance, shown in this top figure here. And systems that have lower species diversity tend to be less resilient to additional stressors. And so it's the likelihood of a system crossing a threshold or a tipping point and moving into a new state increases as species diversity declines. And then, of course, that all translates into things that humans value, ecosystem services, and the more diverse a system is, the more types and different an amount of ecosystem services that are provided. So things like coastal protection, clean water, and food. Disturbances can affect individual habitats, but they can also affect the connectivity between habitats across the landscape. So, for instance, wildfires and flooding can both change the type and the magnitude of subsidies that are delivered from terrestrial systems into aquatic systems. So I'm interested in thinking about how disturbance plays out in a system, and specifically how it changes the physical and the biogeochemical characteristics of the system, and how those cascade down to affect the habitat, and either a single habitat as well as the connections between habitats in a system. And today I'm just going to talk about one type of disturbance, and that's sediment delivery and deposition in coastal systems, and how that changes the individual habitat, but also the connectivity between river, ocean, and coastal habitats. So to set the stage for thinking about dam removals, the US has a long history with building dams. We really got started after World War II, so this is dams built per decade here on the y-axis from 1800 to 2000. And dam building really peaked in the 1960s, early 1970s. And what that means is that in the US, nearly every dam will have reached its lifespan by 2020. So with concerns over infrastructure as well as concerns about how dams are affecting ecosystems, dam removal is becoming more a part of the conversation for river restoration management decisions. So to date, there's been about 1,100 dam removals in the US. Most of these are occurring in the Midwest, towards the East Coast. And many of them are small dams, old mill dams, things like that. But on the West Coast, we've had a number of pretty large dam removals that have occurred over the last decade or so. So we have removals such as Condit in Washington, Marmot in Oregon. You maybe have seen some YouTube videos of those dams being blown up and this sort of tidal wave of sediment propagating down the river. We have some in our backyard. San Clemente is in the removal stage. There are 4 dams on the Klamath that are sort of in a disputed process at the moment, but the likelihood is that those will start coming down by 2020. And then we have the largest dam removal just finished up in Washington on the Elwha and Glines Canyon dams on the Elwha River. So when we think about dam removal, and as dam removal becomes more a part of the conversation, I think it's important to think about the trade-offs of dam removal. So there are definitely desired effects of dam removal, and I think that's what we hear about a lot. So taking the dams out will allow for fish passage of anadromous species in particular. It allows for habitat creation downstream of the dams, as well as restarting that sediment supply conveyor belt that's been blocked by the reservoirs over time. But there can also be unintended effects that can have a lasting legacy in the system. These include things like turbidity, habitat loss, both in the reservoir as well as downstream of the dam, and then just biotic changes within the system. And these different effects of dam removal, both desired and unintended, occur on different timescales. And so depending on where you're looking at the effects of dam removal and whether or not you're meeting your river restoration goals really depends on where in this timeline you're measuring things and where you're looking. And this is really important to think about, in my opinion, because we don't actually know a lot about the effects of dam removals in the long term. So most of the dam removals that have been studied in the US, they have a very short time frame of post-dam studies. So we have 1 to 2 years of usually 1 or 2 points in each of the years following dam removal, and that's it. And so the question really is, do we know enough about dam removals to keep removing them, and is this really a good strategy for river restoration? So we're gonna go to Washington State and talk about the removals that have been happening on the Elwha River. So we are on the Olympic Peninsula here. The Elwha River is about a 75-kilometer long river. 85% of the watershed is within Olympic National Park, which is outlined in green here. It empties into the Strait of Juan de Fuca, just to the west of Port Angeles. And the 2 dams went up on the river in the early 1900s. So the Elwha Dam was built at River Kilometer 8 and was built in 1913. And the Glines Canyon Dam was built in 1927 at River Kilometer 20. And even though it was required at the time that these 2 dams were built, there was no fish passage into the design. So 0, no fish ladders, nothing. The entrepreneur who wanted to build these dams on the Elwha, the goal was to bring industry out to the Olympic Peninsula. And so there were some nods and handshakes made over this deal for fish. There was a hatchery put into the river below the dams, which subsequently failed about 10 years after dam removal, after dam emplacement. So shortly after 1930, all fish were relegated to the lower 8 kilometers of the river. And this is really what was driving most of the conversation about dam removal. So the Elwha River historically had all 5 species of Pacific salmon. Before the dams went in, they had over 400,000 individuals returning a year. At this point, they're around about 4,000, so a decrease of 2 orders of magnitude. There are also 4 species of anadromous trout in the system, and of these 10 species, 6 of them are listed as critically threatened or critically endangered at this point. So that's been a big drive for dam removal. The other part and related part of that is the lower Elwha Clallam tribe and their cultural right to salmon in the system. So the lower Elwha Clallam tribe, their reservation sits at the mouth of the Elwha River, and because of the declining fish numbers over the last 100 years, they've lost their cultural take. So those are the 2 main reasons for pushing dam removal forward. At the time that dam removal was passed into law, the dam was only providing about 10% of power to a single industry in Port Angeles. So even though they were hydroelectric dams, they were not providing a significant amount of the power to the peninsula anymore. So the Elwha Dam came down in 2012, and Glines Canyon Dam came down in 2014. The Elwha Dam took about 7 months to complete and was removed by what's called a staged dam removal. So what that means is just they're very slowly taking down the dam, and for the Elwha Dam, what it looked like was just switching building a cofferdam and switching the side of the river while they were taking down the infrastructure of the hydroelectric power plant and the dam itself. So that one took 7 months to complete. For the Glines Canyon Dam, it took 3 years, the full 3 years that the project was intended to take. And Glines Canyon was it was twice as tall as Elwha. And there was also an issue with the water treatment plant downstream that as soon as the dam was notched down far enough, sort of here-ish in February of 2012, when sediment started spilling out from the reservoir, the water treatment plant downstream was inundated with sediment, and they're providing water to the town of Port Angeles, and so dam removal had to stop completely for about 9 months while the treatment plant got up to speed with technology to be able to deal with that much sediment in the system. So, but still, project completed on time, 3 years from start to finish for Glines. And the reason that these dams were removed by a staged removal as opposed to more quickly or a blow and go type of method was because of the vast amount of sediment that had accumulated in these two reservoirs over time. So for Glines Canyon, her reservoir, Lake Mills, had about 23 million tons of sediment. And the Elwha Dam, her reservoirs, Lake Aldwell, had about 7 million tons of sediment. So Glines was really the effective sediment trap. A little bit got passed into Lake Aldwell. So all told, about 30 million tons, give or take a little bit of sediment in these two reservoirs. And it's a big number, but I think it's kind of hard to sort of picture what 30 million tons look like. It turns out you could fill the Seahawk Stadium 12 times with the amount of sediment that was behind these reservoirs. And initial estimates were that about 50 to 60% of that sediment would move under the power of the river, being eroded and moving downstream. In the first 2 years of dam removal, about a third of that moved, and that third moved actually under really low river conditions. So in the first 3 years of dam removal, we didn't have a 2-year return flood. This winter, we finally had a 4-year return flood. So we saw one event of higher flow. So there's been a tremendous amount of sediment that's moved out of the reservoirs under very low flow conditions. And so these projections of 50 to 60% of sediment might actually be low in terms of now what's expected to move out of the reservoirs in the next 5 to 8 years or so. And this figure tells a story about when that sediment started coming into the river for the first 2 years during dam removal. So over here we have cumulative sediment load in millions of tons, and then on the x-axis again is the first 2 years of dam removal, so from fall of 2011 to fall of 2013. And during the early removal process, there's a little bit of sediment coming downstream, but really that's probably the background level. There's not a lot happening in the system at that point. This first shaded bar here is when Lake Aldwell, when the Elwha Dam was fully removed, and so the sediment could spill out of Lake Aldwell. We see a bump to about 1 million tons or so of sediment moving through the system. That stays pretty calm during the summer. And then once Lake Mills starts to release her sediment out of the reservoirs, when things really start happening. And so we see a jump from 1 to 4 million tons of sediment within about a 6-week period. So lots of stuff moving through, and then by the end of that 2-year period, we had about 8.5 tons of sediment that they could effectively track through the system, past the gauge that's measuring here. And if we look at the suspended sediment concentrations in the river, we see a really similar story. So So little bumps in turbidity early on in the dam removal process, a big bump once Lake Aldwell starts draining her sediment, and then this big extended 7-month period of really high suspended sediment concentration in the river once Lake Mills starts draining sediment. And these, I shouldn't mention, these are proportions of a week in these different suspended sediment concentration categories. And the darker bars are just more suspended sediment in the river. And these values are 2 orders of magnitude higher than what the river was seeing prior to dam removal. So lots of sediment moving through the system in these first 2 years. So this is the largest dam removal in US history to date, and so there's a lot of folks who are working on different aspects of the dam removal project. So people are working in the reservoirs, monitoring the sediment as it moves out. We have river monitoring happening, looking at suspended concentrations, stage changes, coastal estuary, beaches, and all the way out into the near shore. And a host of partners from federal agencies and state and tribal entities as well. Today I'm just going to focus on some of the work that I've been doing in the estuary and in the near shore. So we'll jump into the estuary first. So this is our lovely, tiny estuary complex at the mouth of the Elwha River. So this is what I'll refer to as the east estuary over here, and this little bit over here is the west estuary. And this is what the mouth looked like prior to dam removal. And this estuary, similar to estuaries here in California, are important for a number of reasons. They tend to contain a diverse species assemblage, they're highly productive, they're a nursery habitat for a number of species of fish and invertebrates, and they serve as a salmon finishing schools, especially for Chinook. So as salmon are out migrating, they tend to hang out in these estuaries for a while. Because they're more productive than the river, they bulk up a lot more quickly, and by being bigger when they go out to sea, they can escape some of the predation pressure than if they would have gone out smaller. So important areas for a lot of different critters. And prior to dam removal, we had some sensors in the estuary to look at the dynamics of really the physical characteristics of the system. So these sensors were in a number of locations. The star that's in light yellow there was there for pre-dam and during the first year of dam removal, and it has since been buried, and so we have lost all data from that sensor. But prior to dam removal, the estuary was looking kind of like a typical marine estuary, right? So on the top here is depth for the west and the east sides, and then salinity, again for east and west. And this is for a time period in September. And the orange lines that are going up and down, that's the tide in the Strait of Juan de Fuca. And then in green here is the west estuary, water depth moving up and down, and then the east estuary, water depth moving up and down. And so you can see that this is a very tidally influenced system. Salinity is doing a really similar thing, depending on whether you're closer to the river channel or further away. You're getting inundated by more salinity in that system. If we look at temperature data from a similar time period, we see the same sort of a thing. So this is a thermistor string that was deployed in the estuary over the course of a tidal cycle, and it's just showing that when you get propagation of high tide coming in, you're getting cooler water being pushed in, and then as the tide goes out, you're getting warmer estuary water being pushed back out. And so you're getting this ebb and flow of cool water and warm water going back and forth in the estuary. So again, very tidally influenced system. And then once dam removal started, we had this inundation, a massive inundation of sediment into the system. So 10.5 million tons of sediment eroded out of the reservoirs, 5 million tons or so of that out to the Strait of Juan de Fuca, undetected, unmeasured anywhere else in the river. 3.5 million tons deposited at the delta and in the nearshore, and then just a measly 17,000 tons into the estuary. So if we look at what that sediment deposition looks like at the delta and in the estuary, it looks a little bit like this. So April 2012, Elwha has just come down. Not much of a change in the delta, but over time, the especially once Lake Mills comes out, which is just before this picture, you see that the delta starts moving offshore. And new features are forming out there, and the river's moving around, and things are changing around quite a bit in the system. So we've seen a growth of the delta of about 200 meters at this point, so going oceanward 200 meters. And if we look at what that sediment deposition in the estuary looks like, this is the East Estuary. And for most of the places, what we're seeing is we're seeing at least deposition in most places between sort of a tenth of a foot and a foot in some places, up to meters in other places. So a lot of this habitat here in these back channels especially, we've lost, and they've been completely filled in. If we zoom in a little bit closer and look at some particular sites within the estuary, we deployed surface elevation tables in 2011 prior to dam removal starting, and these are permanent locations geo-referenced in the estuary. And the application of these is usually in marsh systems to look at millimeter to centimeter scale changes in sediment over time. So really, are marshes keeping up with sea level rise is what they're used for a lot. This was not a tool that we needed that precision for. So at most of these SET sites, we saw over 700 millimeters of sediment accumulation in the first 2 years. So again, millimeters, not really the scale we need to worry about. So lots of sediment coming into the system. How does that change the physical characteristic of the estuary? So I'm going to show a series of graphs, and they're all going to take sort of this form. So there'll be the parameter will be on the graph, salinity or depth or turbidity, and then there'll be two shaded bars similar to some of the graphs I showed you earlier, which are when Lake Aldwell starts draining its sediment, and then when Lake Mills is draining her sediment. And these graphs are for the first 3 years of dam removal, so extending out to that third year. So if we look at salinity, early on in the dam removal process, the salinity in the estuary looks like what it was doing prior to dam removal. So it's fluctuating between 0 and 10, 15 PSU. It's looking like a normal estuary. When we get into the winter season and freshet or snowmelt season, that salinity signal from the tide goes away. That makes sense. The river discharge is much higher during this time period. And then, again, as the river calms down, we get lower flows. We see this salinity signal coming back into the estuaries. So not much of a change. And then once the sediment starts spilling out of Lake Mills here, we see a complete and fundamental shift in the salinity gradient of the system. And it has gone completely fresh, and it remains fresh to this day. So those are just showing the ranges of salinity values across the 3 different water years. And we can look at this in a different way and think about what kind of salinity habitats are the critters in the system being exposed to. So in early pre-dam removal, we have a mix of salinity conditions from fresh to oligohaline to mesohaline, and that persists through early dam removal. Again, while when Aldwell starts draining, again, there's less salinity influence into the system, which jives here with those data and the higher river flows. We get some of that salinity back during the summer, but then once Lake Mills starts draining sediment, we lose that signal, and so we've lost this diverse salinity habitat in the system. And we think this is due to the amount of sediment that was deposited between October and December of 2012 once Lake Mills started draining. And that sediment raised the river channel by 1 meter. And so what that means is that the tide wasn't able to propagate as far up the river channel as it used to, and so we lost that influence into the system. If we look at depth, we see a pretty similar pattern. So these really tight cluster of lines early on in dam removal, that's just the depth going up and down with the tides. After Lake Mills, again, when we get that sediment deposition, Depth changes here. We get, for the most part, we start to see a filling of the estuary and a much less variable depth characteristic in this system. And if we zoom in on a couple of time periods, I think this illustrates really nicely the change in the system. So this is the East Estuary, West Estuary, 2012 in red, 2013 in blue, and you can see that we've lost that tidal signal of depth, and the estuary is filling to a degree. So at this point, the depth of the estuary is being controlled mainly by the dynamics of the river. So instead of being a mix of river and tidal influence, it's now pretty much all determined by the river. So when we get filling of the estuary, that tends to coincide with big flood events. When we see low depth levels in the estuary, those are now tending to correspond with a couple of different events. Either the channel has been blocked off by an additional plug of sediment, and so the estuaries are essentially ponds that are totally disconnected from the river and from the ocean. We're also starting to see some braiding of the river channel here at the delta, and so it's moving back and forth with different storm events. And so particularly for the East Estuary, if the main channel of the river moves to the west, there's very little water going into that estuary, and so it tends to drain. And then last summer, we started to see what looked like some influence of the tide and the water depth of the estuary going up and down again. It was pretty short-lived due to our friend, the beaver, who decided to impart a different kind of dam in the system and has effectively blocked this portion of the estuary off from connection to the river. So some new things, new dynamics happening in our system here. And finally, if we look at turbidity, this will be of no surprise to look at this. So we see relatively low turbidity levels in the estuary early in the dam removal process. We see a little bit of a bump when Lake Elwha starts draining sediment, but it's still fluctuating pretty tightly. And then once Lake Mills starts draining, we see a big spike in turbidity levels in the estuary. And not just the maximum values, but we start to see things like this, where the turbidity is high for a long period of time. And so we're not getting that tidal flushing, and so things aren't moving in and out of the estuary as quickly as they used to be. And that pattern continued for the third year of dam removal of those high events. And we can look at turbidity in sort of the classification scheme as well. And these different colors, they are, again, proportion of the turbidity values in the estuary by month for the first 3 years of dam removal. Again, darker colors, higher turbidity values. And I've binned them in such a way that the lightest values are values of turbidity where the system should be able to function normally. So primary productivity, fish, inverts, those guys should all be fine at that level of turbidity. The next color, darker shade here, is at the point where primary productivity in the system can be reduced because there's not enough light penetrating through the water column. And then the third shade here is when fish and inverts can start to be affected by the amount of suspended sediment in the system. So during that period when Lake Mills was draining, there's a big chunk of time when conditions are not great for primary producers or even secondary producers. And those conditions are extending into the growing season. So in 2013, in that summer, we didn't see turbidity conditions clear up until early August. And in water year 2014, those conditions did clear up in June. So we're seeing a shift in when things are clearing up, but we're still seeing these high turbidity values especially during the winter and snowmelt season. Just to give you a sense of what turbidity levels of this magnitude look like, it's essentially like swirling chocolatey mud. It's so dense. It's just a mass of swirling mud really in the system. As I mentioned, when the turbidity cleared up really late in the season in 2013, we had a massive bloom of primary producers in the system. And so we were hauling in lots and lots of benthic algae in particular when we were doing fish seines in the estuary. Interestingly, in 2014, when the water column cleared up a lot sooner, we didn't see that bloom in algae anywhere in the estuary. And so sort of whether that timing was more natural, and so it was a more prolonged growing season, more prolonged primary production over time than in 2013. We're still looking at the samples to see what that looks like. So how do all those physical changes then cascade down to what the biology looks like in the system? So we're looking at a number of different factors: primary productivity, nutrient concentrations, macroinvertebrates that are living in the sediment, fish abundance and diversity, as well as fish diets. So we're puking fish to see what they're eating and how their diets shift over time. So I'm just going to talk about a couple of those things today that we've looked at. So the first is thinking about those invertebrates. Again, we're collecting samples from the benthos. So these are guys that are living in the sediment. And in 2007, which is the pre-dam samples, there's a lot more invertebrates in the estuary, and then we're seeing now in post-dam time. And if we look at what the most abundant taxa are in this system, we've actually seen a pretty wholesale shift in the critters that are in the system. So pre-dam is in blue and post-dam removal is in green. And prior to dam removal, there were a lot of amphipods, ostracods. We had a fair number of dipterans, but really things that like sandy, salty, brackishy places. Once dam removal started and that sediment started being deposited, the community really shifted to be dominated by oligochaetes, so worms that can move through that sediment and that can get out. If they get buried, if there's additional deposition, that they can get out of the sediment. So a pretty big change. We're also seeing freshwater snails start to come into this system that were never seen before when it was a brackish estuary. And then in terms of the fish, what we're seeing is a slight change and a new cast of characters that are coming into the system. So this is salmonids, and this is in catch per unit effort, pre-dam in dark blue, post-dam in light blue. We see some sort of variability around the main salmon species, some variability around steelhead. I would take especially Chinook and coho with a grain of salt. There are two hatcheries on the river. The tribal hatchery is releasing coho, and the state hatchery is releasing both Chinook and coho. So depending on when the hatchery releases are happening and when seining is happening can sort of mess with those numbers a little bit. But what we are seeing is an increase in or first-time appearance of a lot of these trout species. So cutthroat, pinks, bulls, brooks, and rainbows. Some of those are coming from upstream, where there's no dam blocking their way anymore. And some of those we think are just moving into this system because it's now a freshwater system and not salty. If we look at non-salmonids, the big story is just the abundance of sticklebacks that have proliferated in this place. They're sort of out of control. We're also seeing some new players here. Red-sided shiners are a new species that we're seeing. We've lost some of the sculpins as well as starry flounder, which is not surprising given the change in the salinity of the system and the connectedness of the marine system. For non-salmonids, we've also seen a few individuals of shad, which is a little bit concerning. These are an invasive species on the west coast, and they are known to eat juvenile salmon. And so we're kind of keeping an eye on these guys to see what they're doing. Were these sort of some opportunistic strays, or are they actually moving into the system? So for the estuary, I think it's safe to say that we are very much on the side of unintended effects in the system. So we've seen turbidity increase over 2 orders of magnitude. We've seen habitat loss of this brackish estuary through freshening and a fining of the substrate. And we've seen wholesale physical changes in salinity, temperature, and depth in the system. On the upside, we are seeing some new species in the system that are taking advantage of this new, what we're essentially now calling off-river channel habitat. So this isn't functioning as an estuary at this point. And that leads us to the next question and to some future work of what's the future role of this estuary as we have known it. So again, this place is not really the same as it was prior to dam removal, but what about these new areas that are forming out here, these new pools? And the delta is really dynamic, but some of these features are sticking around. So in particular, this pool here has been around for about the last 9 months or so. It's not a great habitat for fish. Fish are using it, but it's open, and so during the summer it gets really hot. There's no vegetation, so the gulls that like to hang out at the delta are sort of fish in a barrel kind of a situation here. So it's unclear whether the estuaries will move offshore over time, sort of in this interim time period, or if we just don't have an estuary in this system until sediment dispersal and deposition starts to stabilize in the system and we get a new, more stable configuration at the mouth. And again, we're doing some additional work with looking at salmon diets in the old estuary to see, sort of, are they getting the same nutrition in this new system as they were in the old system, looking at stable isotopes to look at that shift between marine and aquatic, and then modeling habitat migration on the delta over time. So shifting gears a little bit and moving out to the nearshore, we've been doing work out here since about 2009, so prior to dam removal. And the big stories out here for the nearshore are again, similar to what we're seeing in the estuary. So turbidity is a big deal out here. So the plume for the Elwha River tends to bend to the east due to the currents in the Strait of Juan de Fuca. So if we think about a river plume, oftentimes we think, sort of up and down coast of the river plume should be equally affected. In this case, not so much. Plume moving to the east, we do get reversals in the currents where we get some plume migrating to the west, but mostly to the east. And then we've had, again, 3.5 tons of sediment deposited in the nearshore delta just during the first 2 years, probably another 1 million tons in the last year and a half or so. And that's really changed what the delta looks like here. These are bathymetry surveys of the delta from August of 2011 at the start of dam removal to January of 2015. And so there's not much change that's happening, sort of between August of 2011 and March of 2013. We start to see some formations here, but then things really start happening in 2013 and 2014, and again, this out-migration of the delta is happening. And we're seeing more than 3 meters of elevation change in a lot of these places, some places more. So this star here was the site of one of our dive sites that I'll talk about in just a minute, that was set up in 30 feet of water just off the delta. In 2013, when we went back to resample this site, the boat was in 16 feet of water. Divers got in the water, swam about 50 feet in the direction the transect would have been, and they were standing in 5 feet of water. And at this point, we can walk to that dive site. So just to give you a sense of the scale of the amount of sediment that's coming into the system. So to measure the physical changes that are happening in the system, we've had 2 tripods out in the nearshore in about 10 meters of water, one to the east of the river mouth, one to the west. A suite of instruments on here measuring currents, turbidity, salinity, temperature, photosynthetic light availability, sediment, really lots of anything you can think of. And the biological component is where we've had a series of permanent dive sites set up since 2008 around the delta. And there are 2 control sites that aren't on this map that are 20 kilometers to the east of the Elwha. And you guys, most of you are all familiar with how we're looking at the nearshore at these permanent transect sites. So PISCO-style surveys, fish, inverts, algae along 30-meter transects. And so what we're finding with these guys, just to orient you to these graphs. So these are site names, which don't tell you a whole lot, and I apologize. These guys are our control sites down here. And then this is density number per meter squared of all invertebrates in our surveys. For the bars that are below 0, those are below 0 because we wanted to make a distinction between we actually went there and surveyed and there is nothing there versus we just didn't go there. Okay. So for the starred sites here are sites that have been buried by sediment in the second and the third years after dam removal. So we expect to see, a pretty big change at those sites. We're seeing changes at other sites as well, and this is sort of just to give you a sense of what the substrate is doing across these sites. So in dark brown, those are sites where we've seen a complete fining of the substrate. The lighter brown is where half of the transects have fined, so we see sand on one side and still cobble on the other side. And then in white, those are sites where we've seen no change in the grain size of the benthos. And then again, in blue here, these are our two reference sites. So not really a clear pattern of change in the inverts, whether you look at this change in substrate or not, other than the places that have been completely buried and have gone from cobble to sand. If we look at kelp, the picture is much clearer. So pre-removal in black, and then the 3 years of dam removal. And after the first year of dam removal, we saw 60% loss, at least, of kelp across all species by year 2. For the most part, we had seen 100% loss, except for some of these sites further to the east of the river mouth. And so again, these are sites that were buried. This is the site that we can now walk to, just to give you a reference there. So it's pretty clear, again, that if we look at how the substrate has changed, that it's more than just substrate change, right? It's not just the burial of these sites, or it's not just a finding of the grain size of these sites. And so we're starting to think about what are the other things that are driving kelp loss in the system. So to give you a sense of a scale of change, this is the same site over the first 2 years of dam removal. So Pterogophora, really sad Pterogophora, but no change in the grain size of the bed yet. And then by the second year, we've gone to a sandy system and no live kelp or algae in the system at all. So now we're starting to look at things like light, habitat change, scouring, to think about what else is happening in these systems, and can we explain the change with these other variables. And to do that, we've been looking at the light data that we were collecting on those tripods, and this is just an example of what the data look like. So this is for the same week in 2013 and 2014. River discharge, or river suspended sediment concentration, is in blue. So the solid line is 2013 and the dashed is 2014. And then photosynthetically available radiation in yellow, again solid 2013 and dash 2014. And this mimics what we were seeing in the estuary of that late clear up in turbidity levels of the system. So we get big spikes, we have high suspended sediment concentration in the river, and then we get really low PAR values at our dive sites. And then by 2014, things have really cleared up by early July. So we're seeing conditions where there's a lot of light available for photosynthesis. And this is translating to what we're seeing underwater. So in early September of 2013, we started to see recruitment of small kelps at some of the sites. And by 2014, we were seeing that recruitment at the end of August. So it had shifted a little bit, I think, to match these turbidity conditions that are shifting through time. The other thing that we're doing with the data that we're collecting on the tripods is looking at the photo data. So we have cameras that are taking a picture of the same patch of ocean floor every 4 hours. And so I've gone through these photos and done kind of a qualitative assessment of what conditions look like to try to get at this idea of how often is burial happening, how often do we think scouring is happening, and also turbid conditions in the system. So this is just an example of the photo types that we see. And these 3 conditions can occur within a 12-hour period. So we know that conditions are highly variable in the system. And the way that I scored these photos was as a bare condition here, as a turbid condition here where you can't actually see the bottom, and then a qualitative measure for these types of photos of whether the sediment deposited was at a low, medium, or high level. And I can do that based on how much of those cobbles are buried, essentially, sort of looking at the relief of the cobbles. And so when we look at those data, this is the same time period as the PAR data that I just showed you, and this is just 2013. At the ocean floor, we're seeing conditions that are sort of on par, or that are matching the PAR sensors as well. So we see a lot of turbid conditions, and we're seeing a high proportion of deposition events in this time period as well. So even if spores are getting to these places, I mean, even if they're sort of settling on the cobble when they're clear, it's likely that they're getting buried and scoured away in a lot of these instances. So the next step, I guess this is just a broader picture, so that was just 1 week of time that I showed you, and this is through the 3 years of dam removal. So we see really turbid conditions again when those reservoirs are draining, but a lot of turbid conditions and high deposition events that are occurring during the summer, during that main growing season. And these values coincide with suspended sediment concentration in the river, which is not really a surprise, but we are seeing those turbid plumes that are spanning the whole water column, so full 10 meters of turbid water coming out into the system. The next thing we're doing with these photos is to use some of the other physical measures that we're collecting on the tripod, such as currents and waves, to extend beyond just a single point in space for those measurements. So thinking about what are the current conditions under which sediment is depositing in the system, what are the conditions when it's resuspending in the system, and can we extrapolate beyond just a 4-hour time period and beyond just the point locations where these tripods are. So that's sort of our next step in thinking about where these conditions are occurring and how often. So for the nearshore side of things, again, I think pretty similar to the estuary, still lots of unintended effects in the system. So extended periods of turbid conditions, burial and fining of substrate at many of our dive sites. But we are seeing, with that change in habitat, we're seeing some new species come in here as well. So in places near the delta where we've seen deposition of sandy sediment, we're seeing forage fish coming into the system, sand lance and eulachon, which are important for the salmon and for the whole food web of the Straits of Juan de Fuca. So again, thinking about those trade-offs of what we're losing, but also what we're gaining in the system. And again, I think it's important to think about the timeframes over which these changes are happening. So again, we have a lot of turbidity, but that should be tapering off at some point in time, right? And we're still seeing high turbidity events, but they're shorter and shorter duration. Habitat loss is happening, but the system is in a state of flux. It's changing all the time. And so at some point, these things are going to stabilize. And hopefully, the desired effects of dam removal in this system will be realized, and these unintended effects will sort of move through the system as it stabilizes. There have been a number of surprises in the system that we've seen, which I think are a little bit fun to think about. We've seen an enormous amount of mud in the system. So in the original models, the fine sediment that was in the reservoirs was expected to essentially be blown out of the system and into the straits and dispersed. That didn't happen at all. Largely, that's probably because of the low flow conditions that we had, and so a lot of that fine stuff settled out before it reached the straits. And so trying to get around in the estuary and in the side channels of the river was a little bit dangerous, quite frankly, sinking up to your waist in mud within seconds. So another surprise was the amount of woody debris that came out of the reservoirs. So nobody had thought about woody debris at all, as it turned out. And so this is the eastern beach, so to the east of the river mouth, and there were drifts of woody debris, a meter and a half tall, just completely covering the beach. So the critters living in the sediment probably did not do so well. But it's actually it's created a really great habitat for vegetation, for terrestrial vegetation. And so we're seeing a lot of shrubs and plants starting to sprout in this new sort of mulchy habitat here. It turns out when you lose tidal influence and salinity in your estuaries, they freeze, which was not something we had really planned for in our instruments and sampling scheme. So our estuaries now freeze over for portions during the winter. And I think the other surprise is just the magnitude and the rate of change that has occurred throughout the watershed. And so, we knew there was a lot of sediment in the system, that this would be a big change, but the amount of change that's happened so rapidly, I think, has surprised everyone. So just to sort of pull it all together and sum up, again, thinking about how these disturbances, and in this case, dam removal, but this dam removal in particular is on par with a lot of sediment disturbances from landslides, from human development in different systems, and thinking about how that increased sediment in the system affects physical, biogeochemical, and characteristics of the habitat, I think is really important. And particularly in this system, thinking about how it's likely to continue to respond to additional stressors and what their trajectory of recovery ultimately looks like and how long that trajectory of recovery is likely to last. So with that, I'm happy to take any questions. Yeah.
I guess the first thing that popped up to me
Yep. So we have some surveyor maps and photos from the county that of the delta, and it is somewhere in between where it was before dam removal and where it is now. So kind of sort of somewhere out here-ish. Sort of before dam removal it was back here. So kind of somewhere in between. The delta was much more complex prior to dam removal, and prior to, there are two levees that have been put in. They were put in the 1960s. And to me, looking at those photos, they have changed the shape of the delta the most. Actually, and so this part of the estuary here used to actually be one of the channels of the river. So there were essentially three outlets to the river. One was coming kind of roughly this way, and one was coming through the estuary, and there's a third that was actually coming over here. So it's changed quite a bit just in terms of where things are flowing. It probably won't go back to looking like it did, right? Because there's been some additional infrastructure. There's been blocking off of some of the old river channels up here. So we do have a sense of what it looked like.
Was it mainly a freshwater habitat, or was there was it that estuarine environment that we seem to be losing?
It looks like it was probably influenced tidally. So the locations of, so even though this was the river channel, there were pockets off of it, and the ocean was much closer. So we do think that it was probably tidally influenced at that point, but nobody has data from 1890 on salinity.
Has there been a response of adult salmon return to Elwha?
Yes. So they saw the largest return of Chinook in 20 years in 2013. As soon as the dams came out, they saw fish above the dams. So even Glines Canyon at River Clumber 21, they saw Chinook above the dam, which they weren't expecting. So there's some flow issues and things that they're still working on around both of the dam sites. And the number of reds or nests that have been dug in the river is also increasing quite dramatically, especially in the middle river between where the two dams were. So the first year there were a few reds that were in that stretch, but most of them were in side channel habitats. But more and more are being dug in the main channel, so they're starting to use that habitat, and it's becoming suitable habitat. Yeah.
Do these high turbidity events have a negative impact on the returns?
That is a big concern. They certainly have effects on hatchery fish. So I don't know the ins and outs of the hatchery, but they have done releases of their fish during high turbidity events, and they have lost all of them. They were doing, in the first 2 years of dam removal, they were moving fish actually out of the main channel and into the side channels that were much clearer, because they were concerned about the turbidity conditions.
Your results aren't that surprising.
Yeah.
The results that you're showing, and it seems like those would be predicted. So I'm wondering, what were the predictions for when you thought it was coming to equilibrium, or when it was hot? And then also, how is this informing other dam removals in the northern?
Yeah. So, to the first question, I don't think people expected this for the estuary, because remember, a lot of that fine sediment was expected to go out, and so not 3.5 million tons of sediment. Models can be wrong. A good lesson. The time frame to stabilization for sediment, they think 5 to 8 years after dam removal is complete. So sort of 2019 to 2022, somewhere in there. In terms of the biological communities, hard to say. 50 years, maybe, who knows, right? Depending on where and where you're looking.
What's future, how are they taking these results now?
Um,
Future dam removal.
It's not, at this point, I think the salmon lessons that they're learning are being taken into account. This is a pretty rare case where the dams are located so close to the ocean. So a lot of the coastal and nearshore work, I don't know how well that will translate into other removals. For the Glines dams, that could be a good sort of, model for Glines. But I think a lot of the research that's happening in the river, and if we can keep it going long term, which is unknown, right, will be more useful in informing future dam removals. And I think the idea is here that also if we can't restore a river that's 85% in a national park, can we do it anywhere? Right. So.
If you paired the removal with a high flow water event, would you avoid, do you think you would avoid a lot of sediment accumulation in the area? So is that a possibility for future dam removals?
Yeah, I mean, if you could try to time it with a hydrograph, but right, you don't get a lot of notice of those sorts of things. So.
Have you done any monitoring of upstream habitat from the dam to see if you're getting how that's affecting what used to be a lake that's now back to a river, and what kind of effect that has on the ecosystem?
Yeah, so I'm not doing the monitoring, but there are certainly folks from NOAA that are looking at habitat and looking at fish sort of recolonizing the area. It has certainly changed drastically from going from the reservoir system to the channel system, but it's also really dynamic up there as the river cuts through the old reservoir sediments, and so there hasn't been really an established channel that's set up in either of the reservoirs as of yet. But as of now, the fish are returning. The invertebrate communities have not recovered from sort of prior to sort of where they were prior to dam removal, so they got hit pretty hard by the turbidity system.
So it sounds like less than half of the built-up sediment has been carried down at this point, unless I missed some numbers there. So I guess, and I would imagine that over time, a smaller and smaller proportion of the sediment is going to come down. So do you have any ideas about how long it'll take to work through the backlog of sediment that had accumulated behind the dams? And then, if I can interject a second one real quick. In other systems, given that the sediment and the turbulence seem to be such a big problem, or the turbidity, would it be completely cost prohibitive to dredge the dam before removal and get rid of the sediment before you remove the dam?
Yeah, so sediment stabilization in this system was modeled for 5 to 8 years. At this point, we're about 50% of the sediment has been transported out of reservoirs. And yeah, it should winnow, that amount should winnow over time, sort of as the banks stabilize and they're doing revegetation efforts in the reservoir. So as that gets stabilized, less and less should be coming, and hopefully it will eventually stabilize into a normal sediment supply regime. In terms of dredging the sediment, so that was an alternative that was looked at in the environmental review process, and in this system in particular was prohibitively expensive to try to do that. And the environmental damage caused by building a road and being able to take sort of heavy duty dump trucks and 900,000 loads later. So yeah, it was too much. For other, that tends to be the mode of removal for places where the sediment is contaminated. And they can't just release it. Other types of dam removals